on my mind is in relation to error correcting codes. Uh, I guess one might say, how seriously could one take the idea of quanta and quantum states into macroscopic scales?
Mm, 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 mm.
I think you can take it at least to the scale of gigantic black holes bigger than the solar system.
Is that big enough?
No, you've overshot a bit there.
Does that cover it, Richard? Or
Yeah. Okay, good. I'd like to talk about some scales in between.
Well, no, more seriously, there's this mythology of decoherence that magically happens at whatever the boundary is between the system and its environment. But of course, decoherence is supposed to be an objective physical process, and the boundary between the system and the environment is drawn by us. So the question of how an objective physical process knows to execute decoherence at exactly the boundary that we have drawn is studiously ignored in the physics literature.
So does that mean that
the physics literature around environmental decoherence, or that part of the physics literature around environmental decoherence that treats it as objective? And if it's not objective, then you have to talk about observer relative quantum states.
Okay, I would like to spend the next hour for me to try and understand a little bit of what you just said. That would suit me very well. How does but I don't know what else you had on your agenda, Mike.
Perfect. Let's start with that.
Or yours, Chris, of course.
Yeah. Well, actually, we're going to get to meet in LA in about a week and a half.
Yeah. Yeah, I'm looking forward to
actually in person.
Yeah. So can I try saying back to you what you just said and see how much of it I failed to get? Environmental decoherence, you might need to expand a little bit on what that means. You said that if the boundary between a system and its environment is something that we ascribed as an observer, then the object or system doesn't really know where that boundary is or when that boundary has been violated. So the idea that decoherence is a physical phenomenon rather than something that we project onto it doesn't make sense.
Yeah, that's roughly right.
So an object could have coherence or be subject to decoherence only to another object that sees it that creates, that defines a system of object and boundary and object, environment, and boundary, right?
Right.
So if I was a quantum object, then I could see you as a quantum object. And then you would really be an object and have an environment, and you would do all weird quantum things. But if I'm not a quantum object, if I'm just some sort of, the word platonic comes to mind, but I don't know if that's the right word really, observer, then the whole conceptual framework doesn't make sense.
Right. The conceptual framework only makes sense if you treat all observers as physical systems, which everyone who talks about decoherence at least claims to be doing.
But they're not.
But, well, in classical physics, the observer is basically treated as a god.
Yeah.
Who adopts some view from nowhere that's completely outside of everything being described. And that tradition, unfortunately, was carried over into quantum theory at the very beginning. And so the theory was not applied on principle to the observer, which was treated, as basically a god or a platonic entity or whatever you want to call it.
outside the system.
a bundle of consciousness somewhere. And so if one takes that view, then one has to do one of two things. One either has to, and one wants to explain the fact that these observers receive classical data. Then one has to do one of two things: either modify quantum theory in some way that makes collapse of the wave function or reduction of the quantum state or whatever you want to call it, an objective observer independent process with its own physics, whatever that may be. Or one has to claim that the environment of the system, which is in some ontological sense distinct from the system, interacts with the system. And this interaction removes quantum coherence from the system effectively by transferring it to the environment. So this theory was worked out in the 70s by Zay and Zurich. And the most careful formulation is due to Zurich. He models the interaction at the border between the system and the environment, and on the assumption that the environment is large, and that assumption is essentially always made with respect to the system, then one can just write down the interaction between system and environment in the natural coordinate system for describing the environment. And again, that's a bit of a fudge, because what counts as natural is from the point of view of this Platonic observer. But if you write it down in that coordinate system, which is typically a position coordinate system, for example, then the interaction between the system and the environment automatically puts the system into an eigenstate of position, because the Hamiltonian that's described at the boundary is in position coordinates. And it's the boundary that ends up encoding the classical state of the system and effectively serving as a communication channel between the system and the observer. And this is a theoretical structure that ended up being called quantum Darwinism, because it is based on the idea that the environment will encode multiple copies of the information that's in its natural coordinate system. And values of the interaction that are not in that coordinate system will interfere and dissipate.
Mm.
So the key assumption here is that the system and the environment are in some sense ontically distinct. And that assumption is an assumption from classical physics. It says there's a classical boundary that separates them.
Okay. Hold on a second.
So
did you just say the environment has it constitutes a frame of reference of some kind, a coordinate system, and there are multiple states or kinds of information that can exist in that coordinate system, and the ones that don't exist naturally in that coordinate system dissipate and don't exist?
Right. Are not observable by an observer who's looking at the environment as a bulk.
Right. So I need to do things in a simple way because I don't know the quantum physics or the maths. I wonder if you would indulge me in helping me understand how that might play out for some simple systems, which I think I do understand a little bit better. I have in mind three kinds of system come to mind. One is I'm imagining a rotating body with a light on it, looking at another rotating body with a light on it and what they see of each other when they're rotating at different frequencies and things. I have in mind what one organism sees of another organism when their life cycles are similar or when their life cycles are dissimilar. And the third thing, I've forgotten what the third thing was. Forgotten what the third thing was. Can I start at the beginning?
Yeah, but I think we should back up and look at a much simpler example first.
Okay.
Because it will give you an idea of the sense of the structure of the theory.
Okay.
So imagine a dust particle that's floating around in the air. So the dust particle is 1,000 or so times bigger than any of the air molecules. And there are lots and lots of air molecules. So the kind of canonical picture is you've got this dust ball, my fist, and there are lots of little air molecules hitting it from every direction all the time.
Yeah.
And so each air molecule that hits it strikes it and bounces off. And there's some energy exchange between the dust particle and the recoiling air molecule.
Yeah.
So the standard picture is that constant process, if the dust particle is in a superposition of states, so it's in both of these states simultaneously, then all these dust particles bouncing off of it are going to remove that superposition. They're going to transfer the quantum coherence that makes that state superposed into the bulk of the atmosphere. And in so doing, they'll create a probability distribution of velocities that encodes the position of the dust molecule in the same way that when we shine a light on the dust molecule, this gets a little closer to your first example.
Yeah.
The scattered photons, after banging into it, create a probability distribution of velocities that encodes the position of the molecule. And that encoding is from a decent distance away, so a distance that's much larger than the diameter of the dust molecule. That encoding is effectively classical. So in Zurich's picture, the observers are not interacting with the dust molecule. The atmosphere is, or the light, the ambient photon array is. And the observers are interacting with that environment. They're either measuring sound or scattered light or something like that at some large distance from whatever's going on with respect to the dust molecule. So that's a beautiful theoretical picture, but it does make this assumption that there's a fixed boundary that's known to the Platonic observer between the dust molecule and the atmosphere, that those are distinct in some observer independent way. And the goal of this theoretical approach, and I'm happy to send you a paper about this. It's written for philosophers. It's very old, but it doesn't involve very much technical quantum theory stuff. The goal of this approach is to explain why multiple observers can see the same thing, can measure the same effectively classical state of things like dust molecules, without any prior communication, without any prior conceptual agreement of any kind. And I mean, that assumption can obviously be criticized. I mean, the observers wouldn't agree about anything unless they spoke a common language, for example. So there's all sorts of stuff that's being assumed under the table in this sort of theorizing. So let's now think about your first example and imagine that you just have that the first of the objects is fixed somewhere, and it's observing all the time, and it's observing the other object that's rotating and has a light on it or something. So if it only sees light, then it's just going to see flashes, and it's not going to know anything except, a light is flashing. But if it is also able to observe scattered light at some reasonable intensity, then it may be able to see that there's an object that's spinning, that's flashing, which requires capturing a different chunk of the photon field to do that analysis. So it requires an observer who's capable of, one, sampling a broader environment, and two, doing a lot of computation to distinguish photons that are scattered by this object from photons that are emitted by the object. So the second part of your example, as I understood it, was the observer is actually rotating and its eye is only on one side. So then the observer has to be capable of even more computation, right? Because it sees the thing and then it doesn't see it, and then it sees the thing and then it doesn't see it, and then it sees the thing and then it doesn't see it. So if it's going to regard the thing as the same object, it's going to have to be computationally capable of saying, okay, I'm watching my memory, and now I'm seeing something that showed up previously in my memory, and I'm going to infer that that's the same thing, though there's no evidence that it's the same thing. So that's a pure inference.
So could I just ask there? Yeah, that's really interesting. Is it trivial to know that what you're looking at is your own memory versus primary environment data? Can we assume that which inputs are your actual memory?
Well, it's almost always assumed that it is trivial, but I think from a clinical perspective, it's clearly not trivial, and from a neuroscience perspective, it's not trivial either. Memories have to be somehow labeled as such for the global workspace, or whatever you want to call it, to tell the difference.
I mean, doesn't it also, though, imply the boundary between the agent and the outside world? Because whatever's inside that boundary is memory, and whatever's outside is, environment, right? In order to even treat it as memories. And then you have some kind of stigmergic, in between cases, right?
Yeah. In the formalism that I've developed with Jim and Antonino, we actually treat the memory as a sector of the boundary. And the reason we do that is to allow the memory to encode classical information. So in that theoretical approach, at least, the only classical information around is written on boundaries. So the memory has to be a sector of the boundary. And it may be an internal sector of the boundary. So it may be the boundary between one internal component and another internal component. That's fine. But in order to be classical, it has to be written on some boundary or other.
So who's driving here? Does the memory define the boundary, right? Or does the boundary tell you where the memory is going to be?
The boundary serves as an encoding for the memory. So the system that's comparing memory with current perception has to have two distinct readers. One read operation that reads from the part of the boundary that's the memory, and another read operation that reads from the part of the boundary that's the outside world. And those two readers effectively have to have different names so that their outputs can be labeled by where they came from.
What if the way that I know that this mug in front of me is a mug that I'm perceiving right now, rather than a memory of a mug in front of me, because of the way in which I can interact with it now? So when I remember the mug, I can't manipulate it with my hands in the same way that I can manipulate the actual mug. And when I remember an image, it doesn't move in my head when I turn, it doesn't move in my visual field when I turn my head, same way that an image that's coming in my eyes right now does. Does my ability to interact with it make it, the ways in which I can interact with it reveal the difference between its nature?
Yeah, I think that would work. And that's one way of labeling things, right? As long as you have again, the computational power to associate your motions and your manipulation with the image that you see,
Yeah,
that will work. But you do have to have the computational power to do all the fusion necessary to bundle those things into one event and say that the thing I'm seeing is the same as the thing that my hand is grabbing, which is not a trivial process.
No. But yes, if we took that fusion problem, the sense of fusion problem, as a different problem, then it helps us with the memory versus reality problem, perhaps.
Right.
But perhaps just shoves the difficulty somewhere else.
Yeah, I think I think you have to pay the piper somewhere in terms of acknowledging the computational challenge of.
So where I was going to go,
perception from memory. Yeah.
Where I was going to go with the rotating objects was that if I'm a rotating object with a light on and I'm looking at another rotating object, let's forget about its light for the moment. Then if I'm rotating at a different angular velocity from the object I'm observing, at a very different angular velocity from the object I'm observing, then it might just look like a mess to me. But if I tune in my rotational speed to its rotational speed, then it looks stationary. Sorry. That makes it easy to understand. And what's interesting about that is that it is also appears stationary if I rotate at half the speed of the other object, or any simple integer ratio. But I don't really know. I can't really use my rotational speed, therefore, to determine what the rotational speed of the other object is. It could be any of those that makes it look like it stays still. But also at the in-between frequencies, it's almost like it's not there at all. Like I can't see it at all. It just becomes a blur. And
well, if you're missing it most of the time.
Yeah. So in that respect, the identity of the object, I don't want to use the word coherence because you're using it in a more technical sense than I am, is determined by the match between me and the other object, not the object in isolation.
Yeah.
So if I was an environment that had a particular where a particular combination or assembly of frequencies could live naturally, such as, I remembered what the other metaphor was, such as a guitar string of a particular length. So some frequencies can live on that guitar string naturally and other frequencies can't. An impact on that string, which contains initially a whole different scattering of all sorts of different frequencies zipping up and down the wire, the ones which persist in the long term will be the ones that fit into the length of the wire an integer number of times.
Yeah.
So that's like the, what did you call it? The quantum Darwinism of identifying which states will fit in the environment and which states won't.
Right.
On the right track.
Yeah. Yeah, exactly.
Hmm.
Yeah, the string is a reference frame that can detect particular frequencies, some spectrum. And in a classical setting, you typically think of a noisy input. So the frequencies it can detect are part of the input, but they may be a very minor component of the input.
Mm-hmm.
In a quantum setting, you think of the input being some superposition of frequencies. So again, the frequencies that your reference frame can detect are in there somewhere. And the reference frame responds to those and ignores the rest.
Interesting. So I've been thinking about vibrations on guitar strings and how they interact with one another. And I wonder if I could run that by you, because there's an important conceptual shift. There's a conceptual shift which might be important or might be trivial, and I'd like to get your opinion on it, which is to do with whether this is simply a filtering process, a selection process, as implied by the name quantum Darwinism, or whether there's any transformation involved, that energy can be transferred from one frequency to another, so that you're not just ignoring the frequencies which don't fit, but they're being converted or rotated until they do fit. So the story goes something like, imagine two impulses applied to the guitar string at different locations on the string that create waves which run up and down the string and bounce off the ends and come back again. Now, if their natural wavelength of the wave fits into the length of the string an integer number of times, then they'll be coherent with themselves. So let's grant that for now. But the two waves starting in different places might not be in the same phase with each other. If they were in the same phase with one another, then they would just add up. But if they were completely out of phase, they would cancel out.
Mm-hmm.
But that's not really what happens on a guitar string. Now, I'm going to tell you what happens on a guitar string like I know what happens on a guitar string, but I don't really. But here's what I think happens on a guitar string. If you have two waves meeting each other, same frequency, so they both happily live on that string, but they meet each other out of phase, it produces a kink in the string, which, shall we say, the string doesn't like. It's a high energy local configuration in the string that is going to produce some pushback on those waves. Mm-hmm. And the effect of that is that the string is going to move out of the plane and into another, rotate those waves in another direction so that they can move past each other on the string. In fact, this isn't really just a kink that occurs in one place, because both waves are all over the string and they're creating that kink all over the string, and it's actually making a spiral wave that's going up and down the string instead. And in the process, the one wave that was out of phase rotates around until it's in phase with the other wave so that instead of canceling each other out, the energy from both waves is resolved on the string. Do you buy that story for a start, and do you see the relevance of it?
Well, it's certainly relevant in that the story about exact cancellation, etc., is for an idealized one-dimensional string, quote. Whereas, you're talking about something with a real cross section and elasticity in this torquing direction that's finite, not infinite, and not zero. I mean, in the idealized case, even if you make the string a little bit two-dimensional, it remains ideal or close to ideal if it has zero twist.
Mm.
So what you've constructed is a very much more complicated reference frame that is able to detect a very different range of frequencies, because in a sense, whereas the idealized string would detect kind of a delta function here, and a delta function here, and a delta function here, this string is detecting a big, broad distribution that's created by these finite physical degrees of freedom of the string. So your string is not only moving in 2 dimensions, it's moving fully in 3 dimensions, and it has this extra twisting degree of freedom that an idealized string wouldn't have.
Right.
So I don't know anything about guitar strings, but to the extent that they're sort of finite physical objects with all these extra degrees of freedom, and finite physical objects don't like even the appearance of singularities, and they're going to do something to prevent anything going to infinity.
Yeah. So I think that's when we think about the set of the energies on a string when it's percussed, it's probably a slightly better example than when it's plucked. And how it seems to me that the string, I don't want to make this too much about what actually happens on strings, but it seems to me that the energies in those frequencies are not just filtered to find only the frequencies that are natural harmonics of the string, but they're actually converted through rotations of one wave in interaction with another into the fundamental frequency in its harmonics.
Well, I think in a sense, a better way to say it is that in a physical string, the idea of fundamental frequencies and harmonics are approximations, which have these distributions around them within which a lot can happen. So it looks more like a quantum device than a classical device in a sense, because you could model that possibly as not as a distribution of discrete excitations within this Gaussian envelope, but rather some sort of superposition within the Gaussian envelope.
So it would look like a superposition if you believed it was, or you were measuring it only in that one-dimensional up and down space, right?
Right.
But when you know that, in fact, that there are other dimensions in which it can move, then it becomes non-weird again.
Right.
Yeah. But it's not just that the filtering is sloppy, right? It's not just that the fundamental frequency and some frequencies near to it will live on the string.
Right. Yeah. I mean, if it was perfectly one-dimensional, it would look like a sloppy filter.
Uh-huh.
But as you're pointing out, the thing can also vibrate in this plane.
Yeah.
And it can also actually vibrate in all of these planes too.
Yeah.
Because you have this twisting degree of freedom.
So the reason that I mentioned that is because I think about something that looks like it's an ordinary oscillator, an ordinary one-dimensional oscillator. And it looks like I know what the frequency of it is because I've tuned my laser beam to the right frequency of its oscillations and I've made it look stationary. And then when I start poking it, it starts, it appears to move discretely from one frequency to another without visiting the frequencies in between. But really that's because it's squirming around in a higher dimensional space that wasn't visible in my strobe.
Mm-hmm. Yeah, so I think this story really does generalize very well, and would certainly expect it to generalize to the sorts of measuring devices that evolved systems naturally have, or
right,
evolved measuring devices.
Yeah. So the best
which
thing
are not approximate. You know, they're not the approximations that we describe them as.
Right.
They are things with more degrees of freedom than we've probably measured.
So the best thing to know a guitar string with, to observe a guitar string with, is another guitar string of the same length. That would be able to pick up all of the goings on that are in the first guitar string, and anything that isn't that, anything that just measures frequency F1 and frequency F2 or a frequency spectrum, doesn't have the same ability to, well, I'm tempted to say model what's going on in the string, but it's really just a matter of synchronizing, of getting in phase with, of resonating to what's going on in the string. And that's if you were to try and measure a guitar string with another guitar string that was just the same, you would find that you weren't just observing it anymore, because the observing guitar string would also be producing vibrations that the first guitar string would pick up on. And then they become a coupled system and not just an observer and a system.
Yeah. Yeah. And well, this circles all the way around to the very first thing we talked about, which is that if one models the observer as a physical system, then one's always dealing with a coupled system.
Yeah.
Right. One can no longer idealize the observer.
Yeah.
And this is kind of a hobby horse for me, but we also inherited from classical physics this idea of, well, two ideas. I mean, one of them was that I can interact specifically with one physical system without touching anything else, which clearly requires infinite energy, right? I have to hold the entire rest of the universe at bay so that I can interact with my one thing without touching anything else. And the observer is also considered passive. So the back reaction of the observer on the thing is assumed to be zero.
Yes.
And, quantum theory basically throws both of those out the window, as it should, because they're both unrealistic assumptions.
Right. So you can get good approximations to that, I'm thinking, if the resonant frequencies of the observer and the object are very different from each other and not harmonically related to one another. right? So like the air molecules and the dust molecule, the dust particle, they're very, very different in scale. And so you can treat them as though, one of them is sort of inert and the other one is sort of bouncing off it, right? But that means that you don't really know it that well when you're observing it with a frequency that's very different from what's really going on. And in order to know it better, you have to get closer to the same frequencies and the same harmonics in order to be more sensitive. And as you do that, you become more and more part of the system.
Yeah. Yeah, that's a very good way to say it.
Cool. How are we doing, Mike?
You end up observing an incredible coarse graining along one or two dimensions of interest that you pick.
Yeah.
And
But
ignoring
that's not
everything
far from
else.
saying you can only really see reflections of yourself.
Yeah, which is not far from saying you can only see the things that you're specifically equipped to be able to see.
Which is the things which are exactly like you.
Yeah.
Yeah. Yeah. So that makes sense then of when we think about objects, at everyday physical scales, it seems like they are not doing anything weird, and it seems like we can observe them in a way which doesn't alter anything else, or interact with them in a way that doesn't alter anything else, and that we're passive observers that are not part of the system. But it's not like that when one person meets another person. Why not? It's because the natural frequencies within that person are like the natural frequencies which are in the observer. You can't find out anything about a person without it altering you. And you can't make a person do something in a way that doesn't alter all of their social relationships or holds everything else constant.
Yeah, that's good.
How are we doing, Mike?
Yeah, good. I've been taking notes. A couple of things. If I can get into it, or we can keep going with what you've been doing.
Well, there's one more thing I'd like to try on you, if that's okay, Chris. When two oscillators phase lock in a harmonic relationship, like a 2-to-1 ratio. Hang on, let's start with them being the same frequency first. It's clear that although they are locked to each other, neither one of them is in control. It's not metronome A controlling the period of metronome B or vice versa, that they are a coupled system that has one phase together. And that's true even when you have a 2-to-1 relationship between the oscillators. It's not the case that the fast one determines the two beats of the fast one determines the wavelength of the long one, or the wavelength of the long one forces the 2 beats of the little one to fit inside it, right? In the same way, we can think of those as it's just a coupled system. They co-define the phase of each other.
Yeah, I mean, all this is up to assumptions about how they're coupled together, but right, in some straightforward way, that's true.
All right. So if we extend that from, instead of just a 2-to-1 relationship, to a very small scale to the very large scale, but still phase locked, then the slow scale things would look almost stationary, as though they were just structural. And the fast scale things would look like behaviors. And then if we look really tiny down at the fine scale behaviors, they would look like they were in control, shall we say, and that 1,000 oscillations of this one defines the wavelength of that one. Wouldn't be 1,000, 1,024. And we would be able to look at this system in a bottom-up way about why is the wavelength of this thing 1,000, the wavelength that it is. Well, because it's a period doubling thing going on from the bottom that determined what its wavelength would be. And we would also be able to look at it the other way around and say, well, why are the frequencies on this guitar string the way that they are? They're because of the length of the string, right? The macro scale property is determining the micro scale properties. But it would also be true that in addition to that top to bottom and bottom to top causal communication, that there's stronger communication between an oscillator at a given frequency and another oscillator at a given frequency nearby, right? That I'm imagining now two sort of stacks of oscillators. So each one has this bottom to top and top to bottom communication in determining why is this particular molecule in this particular position can be described at the micro scale, but also at the macro scale. There's a underdetermination depending on which direction you're going, but it's not a zero determination. And then there's also a communication between this particular frequency in this stack and that same frequency in another stack. So that there's I guess I'm trying to circle back around to error correcting codes. So the particular frequencies that can live with one another at one particular scale in this quantum Darwinism way, or perhaps in a transformational way that's less selectionist, prescribe a language of what frequencies are able to live harmoniously with one another at that scale. But they are also have to be contained within a structure that's given by the scale above. That's a lower frequency thing. This is changing more slowly. And they have to be consistent with the higher frequency components of which they are made. They have to fit into them as well. So you have a discreteness, a quantization, which is given by the harmonics, which will fit at any scale. Plus you have these changes in scale from the very small to the very large. And in many physical systems, like a rock, it's as though lots of the middle scales are missing. That there's the molecule, there's the atoms inside the rock, and there's the rock, or there's the atoms inside the billiard ball, and there's the billiard ball. But there isn't any mesoscale dynamical structure that's making good connections between the fast vibrations and the small and the slow vibrations of structure. So to us, they're just inanimate objects. A billiard ball is a billiard ball to other billiard balls, and what are they made of? A ceramic molecule is a ceramic molecule to another ceramic molecule, but those two scales can't see each other. They don't communicate with one another dynamically in an interesting way. But organisms are different precisely because all of the scales in between are also what about them? They're active, they're labile, they are harmonically connected, so that they see each other from one scale to the next. The scales that are very many octaves away don't see each other very clearly. They only interact with one another every 1,000 revolutions or every 1,000th of a revolution, but they're still connected. And that's what makes them organic rather than inanimate. And my question is, how do you like that?
Well, the constraining behavior in living systems is certainly more interesting than the constraining behavior in, for example, billiard balls. I'm not sure that you can say that there's nothing going on at the intermediate scale, right? You have these intermediate scale properties like like elasticity
Yeah.
that are important in thinking about something like a billiard ball.
Yeah. They don't have any
And
error correction at those intermediate levels, though, right?
well, there's error correction in one sense, in that there's at least approximate isotropy of the elasticity across the spherical structure. So, I mean, the ball would behave very differently if its elasticity along the x direction was an order of magnitude different from the elasticity along the y direction.
Right.
And one could think about trying to make such a thing, but
I mean, it
wouldn't
also
work like a billiard ball.
Actually that's funny. The stuff we did on the Physarum that tries to detect where the bigger masses are. Yeah, and it sort of tugs on the medium all the time and reads back the strain angle. We made, as part of that paper, we made a medium that goes in lines of differing stiffness this way versus perpendicular to the thing, to try and so I mean, that's just your anisotropy reminded me of that. But
I want to do Faraday worms on that medium, Mike.
Yeah. It's really not hard, because all you do is what we basically did was this is Narosha did this work where she basically just made agarose gels of different percentages. So some are very floppy and some are quite stiff, and then she laid them out in strips, perpendicular versus parallel to the line between the Physarum and the masses, and yeah, but it's just two things. Just listening to this about the kind of the mesoscale error correction, like Robert Batterman's stuff, and I don't know it super well, but I've talked to him a number of times, and it's really interesting about these kind of mesoscale properties of, he studies metals and concrete and things like that, right? As far as how they dissipate and how do they react to different kinds of forces and strains and all that. I mean, isn't fundamentally part of the issue about error correction is that error itself has to be defined by an observer, and it might be the material itself, but like we think about, what's in our case, we think about what's a developmental error, right? So chemistry doesn't make mistakes. Chemistry just does what chemistry does, but development, we can say, makes an error, but even that's subtle, because certain morphogenetic changes are a birth defect for one species, but they're a perfectly good shape for a different species, right? We've made tadpole tails that look like a different species of frog, and so for Xenopus laevis, that's a birth defect, but actually for another species, perfectly good tail. So what do we think about that at the mesoscale, right? The idea that in order to have error, there has to be an expectation with respect to which things didn't go right or something like that.
Yeah. So
I think that's exactly right. I mean, I think you can only define error or noise or any of these other kinds of properties with respect to some specific observer or even some specific detector or reference frame that observer is equipped with.
But it's sort of one step more than the detector, right? Because being able to measure it is one thing, but actually having the expectation of what you were going to get is yet on top of that, right?
Yeah, that's why I use the term reference frame, since there's always kind of an expectation built into that idea. It's a semantic notion.
I put it to you that there is only harmony. So there is only whether or not this frequency sits well with this other frequency or not. So the way that you can, so the error correction at multiple scales shouldn't be interpreted as that's how you get this macro scale structure with all of this fine resolution exactly so, right? As though it was a blueprint from the beginning. Instead, the error correction at every scale has this underdetermination, right? That there's two ways in which the frequency 1 can lock with frequency 2. And that in between is wrong in so much that it's a high energy stress state and it's not phase locked, but the two ways of doing it are both equally good. Except in the broader context, that one way of doing it fits well with this other thing that was doing it the same way, and this other way of doing it doesn't fit well with this other way of doing it the same thing. same way. And that's those the nothing is right or wrong except in so much as it fits well with another thing of a similar kind, right?
So one question about that I would have is Chris said something very interesting earlier on where he said that physical things don't like singularities and they try to avoid it. So I wonder if that it determines a kind of the singularities and then right is it possible that that sort of thing determines an objective sort of level of wrongness? Like definitely you want to avoid that. Whatever else, all these other things may be equal, but you definitely want to avoid that. And I wonder, and so there's that, and then the related question I wanted to ask, which is this deeply or superficially or not at all similar to the idea of trying to avoid inconsistencies in cognitive systems or logical systems, right? Like, is that similar? The fact that, I mean, kind of a singularity, so to speak, and if you
Exception.
yeah, if you bump into a real contradiction, then you've got problems somewhere. It has to, so something has to give somewhere. Are those two things at all related at all? To me, they seem related.
Yeah, they do seem related. I guess I would say that physical systems avoid singularities because they don't have the energetic resources to actually go to the singular point. So they do something else, right? They as the strain starts to go to infinity, the thing breaks or bends or something like that. The strain never makes it to infinity because that would take way too much energy.
So that's interesting. And I wonder, I mean, maybe Carl Friston would say this is obvious, but that sounds like if you've got two things that seem incompatible, some sort of cognitive paradox, you just don't have the effort to really dig in and figure out what's going on. You sort of give up because it would take too much, right? You avoid it. Let's put it this way, you avoid it because you don't have the energy to really get down to what this implies for the rest of your cognitive structure and all that.
Mm-hmm.
Something like that.
Yeah, that seems very likely. Because it may turn out that it's not a paradox after all, and something else that you thought was perfectly okay is what's paradoxical.
But
that's only like saying, the class XOR is paradoxical because I can't draw a linear boundary that separates them. And if I'm willing to push out into an extra dimension, well, then I can place a planar boundary between them. And you need a higher dimensional conceptual space in order to be able to accommodate all the facts that you have without them contradicting each other. But if you go to too higher dimensional space, then anything is possible. Now all facts are compatible because, 1 is 0 on a Tuesday and 0 was 1 on a Wednesday, and anything is possible if I add enough dimensions. So when the guitar string finds a contradiction that produces a singularity, it causes the guitar string to push out into the extra dimension to enable those things to live with each other simultaneously, to coexist. They can be orthogonal to each other. But as they rotate around, it turns out that was actually the same frequency. It was just in the wrong phase. I just turn it around, and now the string can snap back into a one-dimensional oscillation, and the conflict is resolved. But some combinations of frequencies won't do that. The minimum space in which they can live is still a high-dimensional space. And then, what can you do with that? That's just what it is. There isn't a simplified model to make sense of that.
You get something that doesn't sound very nice.
Yeah, it sounds discordant.
Yeah.
This is interesting, right? It's like, I mean, part of it is I think just active inference, like free energy minimization stuff, right? Where you're trying to make a coherent picture of the world because it's more costly to have one that's full of these disparate, but putting that together with what you just said, Richard. So this ability to push into a new, kind of dimension in order to accommodate these things, right? As a new way to, on the one hand, that's costly to do. On the other hand, you gain because it simplifies a bunch of other stuff, right?
But as you push into the higher dimensions, it's that I don't think that in itself is simplifying, because in the limit you can push into a higher number of dimensions where you just memorize everything and you haven't simplified anything, but you do allow things to at least coexist whilst they're in that higher dimensional space. But if they are compatible, then they can be rotated around so that they then collapse back down into a lower dimensional space, which is what I think you're doing when you do logic resolution. And then, they're not liking the idea of a logical contradiction is only possible in the non-physical system of logic because they don't bend, right? When you try to put true equals false, neither of them give way when they're logical symbols. But whenever they are a physical system representing true and false and you smush them together, they give way, they bend.
So this, and I know I probably bring this up every single time, but this ties to something that some work by Patrick Grimm from the 90s, which I absolutely love, where what he did was he looked at these logical contradictions, so self-referential and contradictory sentences, and the way he allowed them to bend is in time. So what he would do is he would say, well, none of these have a fixed truth value. What happens to the sentences is that it can oscillate. So basically this sentence is false thing just becomes an up down oscillator, right? And so he stretches the whole thing in time, and then he draws them as fractals. So what happens because it's you can plot them as a deterministic chaos kind of thing. And so what he has is these I can send this around. He has these visualizations of either single or double various paradoxical and self-referential sentences where they actually do have a structure, and in this higher space where you don't just try to say, well, it's only got the one thing and therefore we can't handle it because we can't decide which it is. He says, no, there's actually a, if you let it oscillate through time, then it's perfectly compatible. You just have a dynamic structure. And so he basically does exactly what you just said. He gives it an extra dimension, and then these things sort of get resolved, right? But I wonder if we could do something with that, because what he doesn't address is the frequency or frame rate of that oscillation. He just sort of does a tick, the logical tick, 1 per whatever. But I wonder if there's also, if we could make it a little more complicated by giving it a frequency to that oscillation.
Yeah. So that's connects with the inner alignment paper that you were reading this weekend, Mike, right? That the extra dimension that the incompatible states can't resolve their tension, that incompatibility is allowed to resolve by changing their phase, and then when they can change their phase, then they can get their states coordinated. But at the moment, all of the units have the same frequency, so they're just there's only one extra dimension, as it were. But the thing about moving it into the frequency domain is that you could say, well, like in the guitar string, I'll add an extra dimension. Oh, that's not enough either. It's more complicated than that. It's still tied in a knot. It's still making a singularity. Oh, I'll add another dimension. Oh, I'll add another dimension. And that feels a little bit, I'm conscious that we're being recorded. So instead, when you do it in time, you have this, well, I'll move it up an octave. I'll move it up another octave. I'll move it up another octave. And the frequencies in between can't see each other, right? They're just sort of invisible to each other. One wave and another wave of unrelated, not in a harmonic relationship, just cancel out as often as they add up, and they don't have any effect on each other. So you can have multiple things going on. I was going to say at the same time, multiple things going on at the same time, but all at different frequencies that enable you to have sort of multiple dimensions going on, which seem like they're orthogonal to each other. But when you get to the frequency that's a harmonic again, and then they connect up again.
So I wonder what would happen. I mean, this would be easy enough to try. You know, Patrick's got these two sentences that refer to each other, right? Like sentence A is false and sentence B is 0.5, you know, 0.57% true, something like that. And they just sort of make these crazy fractals. But I wonder if if we can set the two sides to oscillate at different frequencies, and what you would then get, right? Because I think, as I recall in his work, the assumption is that everybody goes together. You know, all the truth values are updated simultaneously. But I wonder what happens if that's not true, and I wonder if we can make a more careful link between this kind of like dynamical systems kind of approach that we're talking about now and the logic.
Cool.
You know,
and then go a little bit further to say it's not just that they have it's not just that they're not static, they have a frequency. It's not just that they have different frequencies, but that the resolution of the statements is the phase locking of the frequencies, so that the frequencies adjust and change to one another, right? That's the collapsing back down to the lower dimensional one. So that you end up, if it resolves, you end up with one oscillation, which is the fundamental frequency. And if it doesn't resolve, then you end up with something that's not one dimensional.
So that makes, I mean, that is kind of amazing. It makes a really direct, very minimal system sort of link between these things and really high level cognition, right? Logic and these kinds of things. And maybe these paradoxes do have a resolution. You know, they right, if you play with the frequencies, then maybe there is actually a stable, you know, fact of the matter about what the truth value should be. It's sort of, you know, you can come to a stable decision on that.
Yeah.
We should play with that, I think. Yeah.
I'm enjoying our vibrations. I'm looking forward to meeting you in a couple of weeks, Chris.
Yeah, that'll be very cool.
Very cool. Okay. Good. Yeah, I've plenty of stuff for next time. So I think I'll send around this link to Grimm's work.
Yeah, that would be interesting.
I think there's really something there.
It sounds like the sort of question that's been explored in theories of concurrent processes that run at different rates, but that need to talk to each other now and then. And you want to minimize things like waiting time between processes and so forth.
Interesting.
I mean, it kind of also relates to, I don't know, Chris, I don't remember if I've told you this, but about all this stuff, but the thing that we've been playing with these sorting algorithms, right? And Richard, last time you made the really important point that if they're running at different efficiency rates, then that could explain some of the stuff we're seeing. We've been exploring that. So what we do is we mix, we have these, we're investigating these sort of emergent properties of sorting algorithms, and we sort of make these chimeric systems where two different algorithms are at play simultaneously, and they do have somewhat different rates at which they go, but they're not that different. Like we check that now, and we really paid some attention. So I'll send you some updates on this. But you know, they have a little bit of difference, but it's not that much difference.
So even the insertion operator that needs to go all the way along the list until it finds its place runs in the same time as the bubble sort that only
within. So what we've done is we now, I mean, as you correctly pointed out, we were only looking at one side of we were only counting the one side of we were only counting the moves. We weren't counting the reads, right? So now we do that. And yeah, there are differences, but they're all within 2x of each other. Like they're not, yeah. I'll send you the data. They're not farther than twofold. And it looks like the difference between them doesn't correlate with respect to speed, doesn't correlate with any differences in how they actually segregate. So that's, you know, we're still looking at that, but it doesn't look like that explains it. But anyway, yeah, this I think I'll think more about this. I think we should get back to this issue. This different rate thing is critical.